You're welcome. Like we tried to establish in our previous video that the difference in the LED technologies, the different colors in the LED technology is not as a result of the encapsulation, but as a result of the energy band gap of the the color that is emitting and then the semiconductor material. And then I know that a lot of people may be a bit confused whether to what we mean by wavelengths or frequencies as we've been talking. So I want to just bring it down so that everybody will be carried along. So what we mean when we talk about frequency, wavelength, and all of that. Okay. So I will use the simplest explanation I can give so that everybody, whether a layman, will understand. But I know majority of the people that will understand this concept better are the people in this field, the physics. Okay, so when we are talking about frequency, wavelength, and all of that, what we are talking about, the light as a concept, light, this light has dual nature. So, but basically, let us come from the wave nature. Okay, let's look at the wave nature so that we can explain these two things. This is important. So that by the time we are talking about variations in wavelength and all that, people will be able to follow. So the wave nature we are talking about, just like normal particle, just as a man, you have your two legs, you have your hands. When you move, you can calculate your distance, you can calculate the speed at which you are moving, even a vehicle, planes and all that. But when you see light, how does it move? We try to use the simplest sinusoidal periodic movement of this light to understand the nature of, when we say waving, things are waving. What we are indirectly saying is that the light cannot move just like human being. You have a point, a meeting point, you have where you are going. No, light doesn't move that way. So this is what happens. The light wants to move, it has a source and then the direction. Okay, so when things are waving this way, we've come up to understand that everything we need to talk about this, to describe the nature of this light is already captured in this little diagram you are seeing here, because you can see the top here, it has the peak, then when you go down, it has also the peak from the down below. So this up and down has technical terms, okay, but I don't want to go into the rudiment of all that. I just want to pick these few things so that we can move ahead. This is the amplitude from this minimum horizontal equilibrium position. If you go up, you are talking about the amplitude. When you go down, from here you can still pick the amplitude in this minimum position. And when you pick the crest, from there you see the crest, you see the top. Now, when we mean frequency, word frequency, now let's take this as A and this as B. This is another diagram. See, this is A, this is B. So if you see this, you can see that it takes this thing time to move from here to here. If you time yourself, what is the frequency, the nature of these two? If I ask you now, which one has more frequency? You see that B has more frequency because it takes little time to cover up so many things. If you check from here to here, yeah, it has covered a lot of cycles. So this frequency is higher than this. But the wavelength here, the length of the wavelength, that's the gap from here to here. Gap from here to here is the wavelength. Then you see that the higher the frequency, the lower the wavelength. So let that one enter, so let it sink first so that we can now move ahead. The higher the frequency, the lower the wavelength. The higher the wavelength, the lower the frequency. So this frequency is lower than this one, while the wavelength of this is smaller than the wavelength of this. That's the basic idea we should take in when it comes to understanding what we mean in our previous video by saying nanometer, the wavelength of this, in the frequency of this in terahertz or kilohertz, and so on. So frequency wavelength we are talking about is the gap. See this? I can take another wave diagram. You see this one. You see this. If we enter, this is still classical. If you enter the quantum state of this now, you begin to see a lot of equations, a lot of understanding, trying to extract things from this. Okay, so but we get there, So for the meantime, what we have differentiated is that if the frequency, the frequency is high, then it tells you that the wavelength will be very small. Look at this. So the gap is there. But when the frequency is slow, the wavelength will be very appreciating. But because we are talking about the spectrum, okay? When we say spectrum, what we mean is that we have different EM waves. Okay, these waves can be classified into two: the mechanical wave and then the electromagnetic wave. So light belongs to the electromagnetic wave. So because light belongs to the electromagnetic wave, the EM wave spectrum, that is, if you come to the electromagnetic radiations, the things that are possible, the band, the range, visible light. So among the microwave, there are ones you cannot be able to see and then radiations, there are many things that can come up when you're talking about the electromagnetic radiations. And then you can use this technology to understand it. Okay, so this is the way this has a lot of things. How the microwave, frequency has to increase this order, which means that this one has the greatest frequency. This one has the greatest frequency. This is the gamma wave. Okay, so this gamma, the frequency could be the power of maybe somewhere around 10 to 4. The power of 10 Okay. So when you have this type of frequency, whatever it is multiplied with power, you see that it is very, very big. Then this we're talking about the convert around close to 6, 8, 10 or 12. They are still doing some convert, but now really the one that have long range, the one that have short range, but they are all artificial that still being used. So then you see this place, you have the infrared radiations will be from around 10 to the power 14 to around 16 data power. So this is infrared radiations. So you know this is the CB field, and you know there are a lot of them. So these things you can send your price before you get something that you get to be send it. Then there are also in this range. Then we normally talk about the visible light, which is where we are going to concentrate. So the visible region where you can see, okay, then you now see that so many of these things happens within the visible light. So the visible light we talk about, when we say visible light, we mean white light, white, white light, the one the sun can give you, the sun rays give you white light. Why? Because your eye have absorbed all the wavelengths that is coming from this. So what the eye does, what the eye does is to absorb all the wavelengths. That's why you see white color. But when you disperse this white color, sorry, dispersion I'm using, if you disperse this white color in a prism, maybe a glass prism, because that's another important feature or peculiar characteristic of a light of light. It has to travel in space. It can move in space. It can move in space. That is within a vacuum, and then it can move across a transparent objects. Transparent objects. So transparent objects, those objects like the one we work with on daily basis, the glass prism, the optical lenses you see around, light move through transparent objects. So it's not all the things that move through transparent objects. There are some that when they get either reflected or it can be thrown away. So reflection is not here because light moves through them. So when you bring the white light and disperse it through this place, you have a lot of things happening within this space. And those things that are happening is that the white light that is coming after passing through a prism, which can be either matter the nature of the prism here, because we have a lot of prisms, which when you get there, we begin to bring them one by one to talk about. So when, for instance, triangular prism, white passes, a lot of color spectrum. Remember, we are saying visible light because they are within this region. You see them. And then the one that the wavelength was able to was not absorbed is what you now see. And the brain, the eye, the brain, the retina interprets it as the color you are going to see. So when this white light is dispersed within the triangular prism, the colors that comes out is those ones we listed to you. That is the ROYGBIV. So this is what comes out. Okay, the red light, the orange color, yellow, the green, the blue, the indigo, and the violet. These are colors that comes around, and you see red because it has the lowest frequency. Okay, red because it's going to disperse within some angles. So the reasons behind this is enormous. We may not be going into that today, maybe in a subsequent time when we realize the need. We begin to vocalize these things one by one so that people will see expose all the equations and the calculations within here, you see a lot of things is happening playing around here. So, but for now, what we are saying is that when this white light passes through this glass prism, colors come out, and these colors can be red, orange, you see them, yellow, green, blue, indigo, and violet. And so these are the colors that is possible to be dispersed when you pass through these things. And then because I want to lay emphasis on those two things I, I wrote earlier, frequency and the wavelength. You now see that because the red color has the lowest frequency here, okay, it disperses to a little angle. And then when you look at after the red, you have the orange, to yellow, to green, to these are the different angles of dispersion that is going to come from here, from this interface. Okay, you now realize that in this color, when you gather the range of those colors coming out, you now see that this is a spectrum. This is a color spectrum. So look at let's take for instance, if you want to convert, because some of you may be confused about this nanometer I'm talking about this the other day. Nanometer. What do you mean when you say nanometer? I think I mentioned that yesterday. Nanometer. Nanometer. Some of you may be confused. The nanometer we are talking about, nanometer. This is the unit of which things that, the equivalent of things that are very, very insignificant, very, very little, very, very small. When we talk about those kind of distances, we say let us convert them to nanometer. What this nanometer simply means is to the power of -9. So when we say 620 nanometer, what we mean is 620 times 10 to the power of -9 meters. Okay, once you write this, you put meters. So if you convert this, you know what it means. Okay, then if I say micrometer, what is saying is 10 to the power of -6 meter. Okay, and then this, if you want to convert micrometer to maybe nanometer, you say 1000 nanometer. So 1 micrometer is equivalent to this 1000 nanometer. So, and so on and so forth. So with this, I believe that the mysteries behind what and that the confusion about the frequency and all that is cleared, because it has a relationship that for the color spectrum I mentioned, the red has the lowest frequency. And when it has the lowest frequency, what it means is that in this order, the order I wrote it before, as you move along this order, frequency increases. Frequency increases. So from here to here to this wavelength has the highest frequency. And then when you move in terms of wavelength, you see the wavelength decreases. And then energy of a photon also increases along this. Meaning that wavelength has the higher energy of photon. Okay, so thank you.